Right. So we just talked about the vocabulary for talking about a continuous function at the point A. I don't want to be saying that for every single coordinate, right? So I've previously said things like polynomials are continuous at every single point in their domain. And that's a very useful property, but that's also a mouthful. So from now on, I'm going to say the function f of x is continuous, just continuous, nothing else. And what I mean by that is that for every single coordinate in the domain of f, the function f is continuous at that coordinate. And what that means is we can use direct substitution to calculate limits of this function anywhere as long as we are in the domain of that function. So we actually have seen a lot of continuous functions. The polynomials, the radicals, the rational functions, the sine and the cosine, these are all continuous functions. And they all let us perform substitution to calculate limits, again, as long as we are inside the domain of that function. Now, what's not on my list here, well, a notable exclusion is the piecewise functions. So depending on the formula that my function uses, some piecewise functions will be continuous and others will not be continuous. So again, let's go back to Desmos. Here I have a graph of the absolute value function. And you can think of this as a piecewise function. To the right of x equals 0, my formula is absolute value of x equals x. To the left of my x equals 0, the formula is absolute value of x equals minus x. And right here at coordinate x equals 0, absolute value of x is 0. So this is a continuous function. For the piecewise function, because the formulas are continuous, right? Formula y equals x is continuous, formula y equals minus x is continuous. The different pieces will be continuous individually. And I can say as long as I'm on one side or the other, limits will exist just fine, and I can do my substitution. The only question is what happens at the where the two branches meet, right here at 0. So if I come in from the left, I go to 0. If I come in from the right, I go to 0. That tells me that this limit as x approaches 0 is 0. That matches exactly with the formula for the absolute value function. So the absolute value function is continuous everywhere in its domain, or I'll just say it's continuous. Let's take a look at another piecewise function. In green here, I've graphed a piecewise function, and it splits at x equals 1. So to the left of x equals 1, the formula is y equals x. To the right of y equals 1, the formula is x cubed minus 1. So this is another example where I have a left-hand limit and a right-hand limit. So coming in from the left, my function is tending towards the coordinate y equals 1. That's my left side limit. Coming in from the right, my function tends towards coordinate y equals 0. That's going to be my right side limit. So my two-sided limit here does not exist. Even though the value of the function, if I put in 1, 1 is greater than or equal to 1, so I use the formula 1 cubed minus 1 and I get 0. So this function is continuous at coordinates that are less than 1. And it's continuous at coordinates that are greater than 1, but it's not continuous on its entire domain. So for that reason, this piecewise function is discontinuous at x equals 1. Now, for piecewise functions, you've probably noticed by now all I have to check is whether or not the two different sides of the function line up. So coming in, if I'm going to change this formula, now I've got the formula x cubed for values of x larger than 1. And now I can trace along the whole graph with my mouse with no jumps, no holes. So now this different function, change the formula, I change the function, this is continuous everywhere. No matter where I am, if I want to calculate the limit as x goes to some a, I just find my x equals a on the x-axis. I go up and I find the corresponding y equals f of a. That'll be the value for my limit. So this is another way to think about continuous functions. Continuous functions have graphs that we can draw without taking our pencil off of the paper. Any function you can draw that way is continuous. And so that's going to be a lot of different functions that we work with. Not all of them, but a lot of them.